Let's solve a trig equation. We want to solve 2 sine x over 2 equal 1 over the interval 0 to 2 pi, and then also give all solutions. Let's start by thinking about this interval. What I want is x between 0 and 2 pi, which, if I'm looking at x over 2 in my particular equation, I want to take this interval and divide each part of it by 2, 0 over 2, x over 2, 2 pi over 2, and simplify, and I see that I need x over 2 between 0 and pi. So I'm going to keep that in mind as I solve. Now, coming to the equation, I'm going to isolate sine of x over 2 by dividing each part of the equation by 2, which leads me to sine of x over 2 equals 1/2. I'm looking for x over 2 to be between 0 and pi. Now, the sine of angles that equal 1/2, that are between 0 and pi, are x over 2 in quadrant 1 would be the angle pi over 6, and x over 2, where sine is positive in quadrant 2, would be 5 pi over 6, which has pi over 6 as a reference angle. But since in the end I'm looking for x, not x over 2, I'll take each of these statements and multiply by 2 to isolate x. In this case, here at the left, if I multiply 2 by pi over 6, I end up with pi over 3. In the other case, if I multiply 2 by 5 pi over 6, I end up with 5 pi over 3. So the two solutions that are in the interval 0 to 2 pi are pi over 3 and 5 pi over 3, but I also want to describe all solutions. So let's summarize what we found so far. We found x is pi over 3 as well as 5 pi over 3, but I want to list all solutions as well. So these are the solutions in the interval 0 to 2 pi. To list all solutions, I would list pi over 3 plus 4n pi, as well as 5 pi over 3 plus 4n pi, where n is an integer. The reason I'm using 4n pi is because sine of x over 2 is a sine function with period 4 pi. So, and I should also list these in set notation. Let's solve a trig equation. We want to solve cosine 2x equals cosine x over the interval 0 to 2 pi. What I'm going to do at first is substitute a double angle identity for cosine so that the whole equation is entirely in terms of cosine x, not a double angle as well as a single angle cosine. So for cosine 2x, I'm going to put 2 cosine squared x minus 1. It's cosine double angle equivalent. At this point, I'm going to set the equation equal to 0 by subtracting cosine x. I have then 2 cosine squared x minus cosine x minus 1 equals 0. And I'm going to treat this like a quadratic and factor it. It factors with 2 cosine x, and then I have a 1, so put a 1 and a 1. I want negative 1 as my middle coefficient. So there's a minus, there's a plus, and I've factored. Now I'm going to set each factor equal to 0 and continue from there. So I'm going to set 2 cosine x plus 1 equal to 0, cosine x minus 1 equal to 0, 2 cosine x plus 1 equals 0, cosine x minus 1 equals 0. I'll isolate cosine here by subtracting 1, then dividing by 2 to get cosine x is negative 1/2. At the right, all I need to do is add 1. I'm ready to think about the x's between 0 and 2 pi that solve this particular part of the equation. Now the cosine's negative in quadrant 2 and quadrant 3. Cosine has value negative 1/2 if the angle is, let's see, with a reference angle of pi over 3, in quadrant 2, a solution is 2 pi over 3. In quadrant 3, with pi over 3 as a reference angle, we end up with 4 pi over 3. These two x's satisfy this part of the solution. Cosine x is equal to 1 if x is 0, and that is in the interval from 0 to 2 pi, because the interval does include 0. So the solution set for this particular equation is 0, 2 pi over 3, 4 pi over 3.
Solve the equation 4 sine theta cosine theta equals the square root of 3 over the interval 0 degrees, 360 degrees. So let's begin by rewriting the original problem. 4 sine theta cosine theta equals the square root of 3. We're going to rewrite 4 as 2 times 2, because then we can use the identity that 2 sine theta cosine theta is equal to the sine of 2 theta. So we begin 2 times 2 sine of theta cosine of theta equals the square root of 3. And now we rewrite 2 sine of theta cosine theta as the sine of 2 theta. So 2 times the sine of 2 theta equals the square root of 3. Now divide both sides by 2, and we get the sine of 2 theta equals the square root of 3 over 2. First of all, the angle whose sine is the square root of 3 over 2, or at least the angle in the first quadrant, would be 60 degrees. So we know what we're going for here, but what we have to remember is that the original interval from 0 degrees inclusive of 0 to 360 degrees exclusive for 2 theta would actually be from 0 less than or equal to 2 theta less than 720 degrees. So this is the range that we're looking for, the values for theta that satisfy this. Well, again, we said that sine, which is positive, is in quadrants 1 and 2. I already said that, therefore, one of the values would be 60 degrees. The equivalent reference angle 60 degrees in quadrant 2 would give us an angle of 120 degrees. But again, for 2 theta, we're going to go all the way up to 720 degrees. So we add 360 degrees to 60 degrees, gives us 420 degrees. And then we add 360 degrees to 120 degrees, and it gives us 480 degrees. But now to solve for theta, we would have to divide the left-hand side by 2, and then each of the corresponding degree values. So theta is going to be equal to 30 degrees. 120 divided by 2 is 60 degrees. 420 divided by 2 is 210 degrees. And 480 divided by 2 is 240 degrees. The other way of looking at this is that these final two solutions for the 2 theta that we found by adding the 360 degrees to each of the 60 degrees and the 120 degrees. And so we can write out the solution set as 30 degrees, 60 degrees, 210 degrees, 240 degrees. Let's look at another part of this example. Solve the equation 4 sine theta cosine theta equals the square root of 3 for all solutions. Well, remember, we had solved this in the interval from 0 degrees to 360 degrees, and the two angles that we were dealing with were 60 degrees for 2 theta and 120 degrees for 2 theta. So now remember, to find all solutions, we add multiples of 360 degrees to each of the original two solutions, which were in quadrants 1 and quadrants 2. So therefore, we add 360 degrees n. 360 degrees times n. But of course, we want just theta, so dividing through by 2, we get theta equals 30 degrees plus 180 degrees n. And here we get theta equals 60 degrees plus 180 degrees n. And so when we write out the solution set for all solutions for the value of theta, we would write it like this. The set 30 degrees plus 180 degrees n, comma, 60 degrees plus 180 degrees n, comma, where n is any integer. And that's our solution set.
Let's solve a trig equation. We want to solve tan 3x plus secant 3x equals 2 over the interval 0 to 2 pi. Well, I'm going to start by isolating tangent, subtracting secant 3x, and then squaring both sides of the equation. So doing my first step, which is to subtract secant 3x, I get tan 3x is 2 minus secant 3x. Now I'm going to square each side of the equation. I get tan squared of 3x on the left, and if I multiply out the right-hand side, 2 squared is 4, minus 2 times 2, which is 4 secant 3x, plus secant squared of 3x. And I'd like to have entirely secants or tangents, so for tan squared of 3x, I'm going to substitute the Pythagorean identity, which is secant squared 3x minus 1. And that's equal to 4 minus 4 secant 3x plus secant squared of 3x. I see at this point that I can subtract secant squared of 3x from each side of the equation. I'm also going to subtract this 4 from each side. That'll give me negative 5 equals negative 4 secant 3x. I'm going to divide each side of the equation by negative 4. I'll end up with secant 3x is equal to 5/4, and I'll want to continue from there. So I'm at the point where I have secant 3x is equal to 5/4. I'm going to use the reciprocal function for secant and say that if secant 3x is 5/4, then cosine 3x must be 4/5. And stop for a minute and think about the fact that I want x in the interval 0 to 2 pi. However, in this equation, I'm looking at 3x. So I'm going to take my interval and multiply each part of it by 3. 3 times 0, 3 times x, 3 times 2 pi, which tells me that 3x should be in the interval 0 to 6 pi. So that tells me the types of values I'm looking for. Now there isn't an exact angle whose cosine is 4/5. So to get 3x, I'm going to have to use a calculator and use the fact that the cosine's positive in quadrants 1 and 4. So with the help of a calculator, and the calculator needs to be in radians, I'll find the inverse cosine of 4/5, and that leads me to the decimal 0.6435, and I've rounded to the 4th decimal place. Now, that's an answer, an angle in radians that's in quadrant 1. I'm going to use it as a reference angle into quadrant 4, so I would subtract it from 2 pi and come up with 5.6397. And there are two solutions. But I can keep going because I can give all answers up to 6 pi. So what you can do is go ahead and add 2 pi to 0.6435, and that'll lead you to 6.9267. Add 2 pi to this value, and you'll end up with 11.9229. And we're going to keep going. 6 times pi is 6 times 3 and so forth. So we can keep going until we get to more than 6 pi. So adding another 2 pi, or maybe adding 2 pi to this, I would add 4 pi to 0.64. I end up with 13.2099. Adding 2 pi to this, I end up with 18.2061. And I'm going to stop at that point, because if I add another 2 pi, I'm going to be more than 6 pi. And I found some values for 3x. I want x, though. So I'm going to take each value I found and divide them by 3. Each one divided by 3 lead to decimals, 0.2145, 1.8799, 2.3089, 3.9743, 4.4033, and 6.0687. So I have these 6 solutions. The only problem is I squared both sides of the original equation, and so there was the chance to introduce an extraneous root or extraneous solution. I need to take each one of these 6 solutions individually and check them in the original equation. If you do that, you'll find that they are not all solutions. The solutions, or the values that check, are this value, the 2.3089 checks, and 4.4033 checks. And let's summarize our solutions to this particular equation. The solution set is 0.2145. It also contains 2.3089, and it contains 4.4033. Let's work an application problem. Suppose that the A key above middle C is played. Its fundamental frequency is F1 equals 440 Hertz, and its associated pressure is expressed as P1 equals 0.002 sine 880 pi t. The string will also vibrate at these other frequencies, 880, 1320, 1760, 2200 Hertz. Continuing, the corresponding pressures of these upper harmonics are as shown. Here's P1, P2, P3, P4, and P5. Well, it turns out that the graph of the sum of the 5 pressures is sawtoothed, and you can see a picture of how that graph might look here. And again, what's graphed is P, which is the sum of the 5 pressures. Well, here's the first thing we want to do with that graph. We want to find the maximum value of P. So let's use our calculator to help. We're going to go to our calculator, and what I've done ahead of time in y equals is I've entered, and it's hard to tell maybe, I've entered P1 plus P2 plus P3 plus P4 plus P5. I've set a window that matches the window shown on the graphic. It's 0 to 0.1 in the x direction. It's negative 0.005 to 0.005 in the y direction. If you push graph, you'll end up with this same sawtooth wave. Now, the question was, what is the maximum value of P? I'm going to use the calculator to help. So I'm going to go to Second Calc and option 4, which asks for a maximum. Recall that how the calculator works is it asks you to put a left bound and a right bound on your max. So I'm going to look for the max here at the center of my graph, entering for the left bound, and then moving clearly to the right and entering for a right bound. And maybe I'll move just a little closer and say that that's my guess, and let the calculator run its program. So the maximum value is the y-coordinate, which is 0.00317 if you were to round to the 5th decimal place. Note that it occurs at x equal 0.0047. And another question that's useful, because the max is the same for each of the peaks of this sawtoothed wave, is to get the x coordinates for each of the maximum values. And I've done that already, and I'd like to write them down, and you can check this with your calculator. First, let me write down that the maximum value of P that I've found is that 0.00317. It occurs at x equal, let's see, if you find those values, you'll find they are 0.000188. It also occurs at 0.00246. It occurs at 0.00474. It occurs at 0.00701. And it occurs at 0.00928. And it's a good idea to check that these are the x's for which y comes out to 0.00317 with the help of your calculator.